So we'll wait another 1 minute. We'll get started. Everybody's a J so far. Amazing.
It's not a coincidence. We're the best, sir.
I guess so. Well, you guys at least have the gumption to show up. It's pretty impressive. There'll probably be some people join later, but anyway. All right, I'm gonna go ahead and get started. So first, let me just let me bring up the browser and the websites. Okay, hang on here. I'll share my screen here in 2 seconds. All right, so if so let's see. I don't know which sheet. Yeah, where is it? Oh, okay, yeah, here. So let me stop share. I wanted to share a different screen. Okay, so let me share the screen, and what I want to share is this one. Okay, can you all see this?
Yes, sir.
Okay, yeah, somebody, Daniela, maybe you should, if you mute your microphone, we're hearing a lot of background noise. Yeah. Okay, so if everybody looks at this screen over here, the one I'm sharing, so this is 2513B, but if you go down to the videos F21 and S22, click on that. If you go down to the bottom, there's a Zoom review for F21. There's a, I think this was a Zoom review for S21. There's another Zoom review probably for before then. Then there's a YouTube lecture, which was a Zoom review for online final exam. Then there was another one was just a straight review, wasn't an online review. And then another one and another one. And that was it. So any of those, it could be reviewed. They'll probably help you. And then if I stop share and, or actually, I'll go back and share. Well, I'll switch to the A section. And I'll share a screen again. We'll do this one. Go over here. So if you see this one and you go down to video lectures, videos F21 and S22, and you click on that and you go down to the bottom, it's basically the same thing. A Zoom review, a Zoom review, a Zoom review, a Zoom review, another Zoom review, and then several lectures that were just reviews. So there's 1, 2, 3, 4, 5, 6, 7, 8, 8 hours of reviews. So you can, so either group, either the A or B course can pretty well see what they need to, plenty of material for review. So the final will be on Tuesday. So I guess tomorrow's the 5th, the 6th. So it's going to be the 6th, all day on the 6th. And I'll give you a good 2.5 hours to do it. There are 100 questions. So that's more, minute 20 a question, basically. But some of them a lot of them won't take anywhere near that time. There will be an associated figure, just like on the first 2 tests. And probably ought to pull that down and look at that first. And then start answering the questions. You will have to start the test though to look at the figures. All right, so here's the test we're going to work. I did print it out, so I'm going to work on it on paper over here. So let me just switch to that. Let's see. So yeah, so here's the test, and then I'll switch off. So this is it. And so I will do full screen mode. So you can see, and we'll go through this whole test. Okay, and then I do have, I will switch it over here instead, and we'll do this one. Okay, that should be good, I think. So can you all see this okay over here?
That looks good.
Okay, great. So the first ones are just, let me switch my headset. And I should do the little inset, but I won't. Maybe I will. Well, no, let's see. I guess I could. Well, that's okay. No reason to do that. We'll come back and do that in a minute. All right. Okay, so so this first one is it's in POS form, and you got supposed to go to SOP. There are just two of these, no big deal. I think there are some, there are not too many, and so we won't spend too much time on this, but the first thing to do is to look at your simplification theorems and see if you can simplify it. And indeed, you have an AC here and an ACD there. You can get rid of that using the I think it's S3. And then here we have, so what we're left with then is A plus B plus C prime times A plus C. I just rearranged that. That term's gone. And so A plus B plus C prime. So a good way to do this is with M and F using the C prime and the C. And that gives us C times the quantity A plus B plus C prime times A. And then we just distribute that in, and we get CA plus CB plus C prime A. And then we can combine these two to A. And that just gives us A plus CB. This one, very similar. So, and for this one, we use the first, we used S1 for this one. We used S2 or S3 actually for this one. And then we used the conversion 3 for this one, which is the multiplying and factoring theorem to go from here to here. All right. So let's do this one. So we have a ABC, we have an ABCD prime, we have an ABC prime, and we have a B prime CD. So the ABC prime and the ABC can certainly be combined to reduce to AB. So that gets rid of these. So now we have AB plus ABC D prime plus B prime CD. Now we have an AB and an ABCD, so we can get rid of this term. That gives us an AB plus B prime CD. And now we can just kind of use the B and the B prime, use the C, the conversion theorem 3 again, and work backwards. And so we just do this with this, and this with this. And so that gives us the quantity B, the quantity A plus B prime times the quantity B plus CD. And then we can use this, we can use conversion 2, the second distributive law, to simplify this using X and Y, Z. And so that'll be B plus C quantity times B plus D. And then this is just A plus B prime. So those are pretty simple. And I'm not even sure actually what shows up on the test. I have to look. I don't think it's any, I don't think there may be just some real simple conversions. Okay.
Could you go over the second step again?
On this one? Yeah, so
I understood the first cancellation where you got
so we
AB.
combine these and we get AB. And then look,
Yeah,
we've got an
after
AB in
that.
this term. So we can use the, so now we can use the, and we actually had an ABC here anyway. We just could have killed that from ABC and ABCD prime. But now we have an AB, it's easy to see. Does that make sense?
Go over it one more time. I'm sorry.
Yeah, so we have A, B, C here, and we have A, B, C, D prime. So we can use S3, the simplification 3 theorem, which is basically, that's just X plus Y times X equals X.
Okay.
Or actually, sorry, I gave it to you in POS form. XY plus X equals X.
Okay.
So this one goes away because you've got the X and the X here. The extra terms don't, the extra literals don't matter.
Yeah. Thank you. I was missing that.
Okay, no problem. All right, so we'll take the truth table and plot it. This should be like falling off a log. So 0, I won't write the zeros. So 0, 1, 0, 0. I'll divide it into 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so a 1 and then 0, 0, don't care, 0. 1, 1, 1, 1, and don't care, 1, 1, don't care. So this is pretty simple. You do all that, and then we also have to get this one, and then there's an, you could do this, but those are both don't care, so that's kind of silly. So our SOP solution then, is, this is just going to be A, and this would be B prime, A prime, B prime, C prime, D, B prime, C prime, D. And then this term, which you don't really need, would be B, C, D. All right, so our SOP solution is going to be A plus B prime, C prime, D. And then our POS solution, so we'll take off, we'll still put in the don't cares, put in the zeros. So 0, 0, 0 here. And then zeros there, there, and there. All right, so it looks like we'll do this column, do this group of 4, and this wraparound group of 4. And then you could also do this one, and I guess you could do this one. So the SOP, but you don't need those. So we just need this column, this group of 4, and this group of 4. So if they were ones, then I'd write this column would just, the column would just be A prime B. That turns into A plus B prime, because they're zeros, not ones, so we have to invert it. Then this wraparound group would be D prime, it would be D prime, A prime. So that would be D prime, A prime, which turns into, A plus D. So we're going to have A plus D quantity times A plus B prime quantity times, and then so then let's see, so we got this column, we got this wraparound group of 4, and then this group of 4 here. So if those were ones, that would just be A prime C. So instead it's going to be A plus C prime. So that's your POS solution. And clearly this is simpler. Only 3 gates instead of 1, 2, 3, 4 gates. Okay, any questions with that one? All right, so I won't spend a lot of time on this code because you can't see it. So maybe well, it's not too bad. All right, so so this is in VHDL instead of Verilog, but it's very similar. Remember, instead of process, we use always with an @ sign, and then we have our sensitivity list, same thing, only we use pos edge and neg edge. So we would write for this, we look at the clock. So Yeah, I'll give you the right diagram as far as the clock goes anyway. So you can see, or this would say, I think this is a pause edge. Yeah, it's a pause edge. So what this should be, it should be the sensitivity list. Well, I'll just write it. Actually, I have it written. Hang on. I think actually I have it. Yeah, you know. Yeah, maybe I guess I threw that away and it's gone. Never mind. Okay, so that would be always at and then it would be pause edge. CLK. And then it would be neg edge. Let's see, what do we have? We have a set, we have a clear knot and a set knot. So it'd be neg edge. Clear knot. So neg edge set knot, neg edge clear knot. Sorry, I kind of ran out of room there. Okay, so and then the rest of it's going to be the same. We'll have a begin, we'll have if the clear knot equals 0. In this case, you don't use the then keywords, not there. We just do if and then parentheses around that, and then temp equals 0. And we just use the same thing. We use for Verilog, we use the less than equal. We also use that in VHDL, same thing. And then so first we test the clear knot. If it's 0, then we set the temp to 0. Then we test if it's 1, then we do the else if. We test the set knot. If it's 0, then we set temp to 1. And then if both clear knot and set knot are high ones, not zeros, then we do the last else if clock tick event clock equals 1. This is just an idiom in VHDL for pause edge, basically. And so ignore that. In Verilog, we just write an else clause here. Else temp equals D. Remember, the left side in Verilog has to be a register. So we would have declared temp, an internal signal, which would be a register. And you see that here in VHDL, we do basically the same thing. We have a separate description of the port list, and then we have the actual structure of the module. In Verilog, we just combine them into one module definition, but it works out to be very similar. Anyway, so and then we have the end of the process block, or the end of the always block. In Verilog, we just say and. So basically, we have a clear knot that is asserted when it's 0, which makes sense, and a set knot that's asserted when it's 0. And otherwise, we have a positive edge clock. And when the clock ticks, if those aren't active, those aren't asserted, then D will, whatever D is what the flip-flop will go to. So what kind of flip-flop is it? It's a D flip-flop. How many different states? It can remember 2 states, 0 and 1. Will the process block execute on a change in D? No, because D is not in the sensitivity list. We have clock, set knot, and clear knot in the sensitivity list, but D is not there, so it won't trigger the always block to execute. So no, and that's because D takes effect on the clock edge, not when it changes itself. Is the clock rising or falling? So in this case, there's no bubble and it is rising. Then label the blanks A, B, C, D. So the C is the D input, and here it's CLR not and SET not. Could be either way, it doesn't matter which way you put them. And then add bubbles. Okay, so these are active low, they have to have bubbles, but the clock is a rising edge clock, so it doesn't get a bubble. If clear knot equals 0 and set knot equals 0, then what does Q equal? Well, the clear is tested first, and if it turns out to be 0, then temp will be 0, and then down here Q will equal temp, Q prime will equal not temp. So Q would be 0. You would never test the set if the clear is asserted, regardless of whether the set's asserted or not. You only test the first one, and if it's true, you don't test the else ifs at all, or the else, obviously. Okay, I'm not going to go through. I'll do I kind of did these in class, and I'm not going to do this because I'm not going to really ask you the two's complement thing. I don't think it's even on the test, but if it is, you can use it. You can use a calculator to figure it out. Just remember, you have to pad out to 8 bits. So for instance, what's the biggest number, or how many bits for positive and negative 46? So if you have plus 46 and you want to represent minus 46, how many bits do you have to fit plus and minus 46 into the? Can somebody tell me?
91.
Anybody want to take a guess at it?
Well, 91.
So we know so you can just work backwards. Okay, so what's the nearest power to? Well, 64. So plus and minus 64, which is 128. So we would have to have 7 bits. 8 bits would be 256, but we don't need that many. But we do need plus and minus 64 to cover our plus and minus 46. All right, I'm not going to do the multiplication or the subtraction. I don't think those are on the test anyway. All right, let's take a quick look at this one. So obviously we group these, we group those, that solves the problem. And so if we want to draw the circuit, we would know that this is going to be B, D, and this one's going to be A prime, B prime, C. Okay, but there is a consensus term right here, which you could add to fix a hazard. And that consensus term is going to be A prime, C, D. Okay. And the transition that could give you trouble would say be transition from here to here or from here to here. Okay. And that depends if you have to use an inverter. All right, let's look at this one. Okay, sequential circuit has an input X and an output Z. The Z equals 1 if the two previous inputs were the same, and 0 if they were different. See the example data, and then complete the state table and graph. Note when specifying the previous inputs, the order is 2 clock cycles ago, 1 clock cycles ago. So thus the previous input 0, 1 means 2 clock cycles ago it was 0, the last clock cycle it was 1. So on the graph, use a slash between input and output because it's a mealy. So we're doing a state graph. All right, so this is a little example sequence. We assume it's that the input's been 0 before the clock, before we start looking at it. Have to make some kinds of assumptions, so we'll assume. So we're going to start in S0. If it were some other pattern, we'd have to start in the correct node. And in this case, since we know there are 4 different possible previous states we have to remember, we know we're going to have 4 nodes. We have to remember the previous 2 were 0, 0, or the previous 2 were 0, 1, or the previous 2 were 1, 0, or the previous 2 were 1, 1. And then what we want to do is we want Z to be 1 if the 2 previous inputs were the same. So in this case, we want, when we're leaving this node, we want Z to equal 1. When we're leaving this node, we want Z to equal 1. But leaving these 2 nodes, we know that Z has to equal 0, or we can just write Z prime. Z prime would equal 1, obviously. Okay, so let's do this. So we started in state 0. The 2 previous inputs were 0, 0. If we get a 1, now our 2 previous inputs are 0, 1, and we have to remember that. But we have to output a 1 because the 2 previous inputs were the same. If on the other hand, we get a 0, we output a 1 and we stay here. In this node, whenever we leave, we know that Z will be 0. So our output will be 0. If we get a 1, then the 1 will shift over and we'll add a 1. So we'll be in 2 previous inputs are 1, 1. And we'll output a 0 since the 2 previous inputs are different. If on the other hand, we get a 0, then now we're 0, 1. So we'll just go here on a 0 and output a 1. In S3, we have 2 1s. If we get another 1, we're going to stay here and output a 1. If we get a 1, because they're the same, Z has to equal 1. If we get a 1, I mean, sorry, if we get it, even if we get a 0, we're still going to output a 1, and we're going to go here on a 0, and we'll output a 1. And then if we're in S2, if we get a 0, then our last two inputs are going to be 0, 0. We're going to go back here, and we'll output a 0 because they're different. And if we get a 1, then we're going to go here on a 1, and we'll output a 0, because then the last two inputs will be 0, 0, 1. But we still have to output a 0. All right, so that's that. And then it's easy to fill these in. For S0, if we get a 0, we stay. If we get a 1, we go to 1. From 1, if we get a 0, we go to 2. And if we get a 1, we go to S3. From 2, if we get a 0, or sorry, a 1, we're going to 1. And a 0, we're going to S0. On a 1, on a 1, we're going to S1. And on a 0, we're going to S0. And then from S3, on a 1, we're staying at S3. And on a 0, we're going to S2. And here's our output. We have a 1 there and a 1 there, and a 1 there and a 1 there. All right. So this is our non-sequential count sequence with no repeated terms. So 3, 7, 1, 2, 5. So no repeated terms. That's fine. So we'll just use 3 flip-flops, and we'll list them out, and we'll just fill them in. So if we're in state, if we're in 0, 0, 0 for our 3 flip-flops, that's not part of our count sequence, so it's a don't care. If we're in 1, we go to 2, 0, 1, 0. If we're in 2, we're going to go to 5, 1, 0, 1. We're in 3, it's a don't care. If we're in 4, that's also a don't care. We're in 5, we go back to 1, 1, 0. If we're in 1, 1, 0, we go to 1, 1, 1. And if we're in 1, 1, 1, we go to 0, 0, 1. All right, now we just put these in. X, 0, 1, don't care, 1, sorry, 1, 1, 0. So we'd have this and that. So this is just going to be C prime, and this group of 2 is going to be A, B prime. So C prime plus A, B prime. Okay, then this next column, X, 1, 0, don't care, 1, 1, 0. So it looks like we're going to do this and wrap around that. So that's going to be B prime plus, and this would be A, C prime. Okay, and then this one, don't care, 0, 1, don't care, 0, 1, 1. So that's just going to be this, and that is going to be B. So DC is just B. And that's all there is to it. Any questions about that?
Can you go over how you got the next states again, please?
So we take it from our count sequence right here. So we know if we're in state 1, 1, 0, our next state would be 1, 1, 1. If we're in 1, 1, 1, our next state would be 0, 0, 1. If we're in 0, 0, 1, our next state would be 0, 1, 0. And if we're in 0, 1, 0, our next state would be 1, 0, 1. Now, I just ordered them in binary order. You could, if you want, you could start with the rows. You could start with all the. You could start with them. You could set it up like this: 1, 1, 0 is going to go to 1, 1, 1. 1, 1, 1 is going to go to 0, 0, 1. 0, 1, 0 is going to go to 1, 0, 1. 1, 0, 1 is going to go back to 1, 1, 0. And then we happen to know, so we're accounting for, so we've accounted for 6, 7, 1, 2, and 5. So we know 0, 3, and 4 are going to be don't cares. So we put 0, 0, 0, don't care. 0, 1, 1, don't care. And 1, 0, 0, don't care. Now you take these rows and you just rearrange them by this column in binary order, and you get this. So I just started out with them in binary order.
Oh, okay, that makes more sense. Thank you.
Okay. And then all you do is extract your next state for A, B, and C. Those are your D, those are your DA input, your DB input, and your DC inputs. And you have 3 flip-flops, A, B, C. There's really no, does this circuit have an input besides the clock? No. There's no input, and there's actually no outputs. It's just the flip-flop state. All right, everybody good with that? Okay, so this problem is you're to finish a state machine chart for a problem with an input X and an output Z, where Z equals 0, except when the target 101 is detected. So there's our target, 1011, rather, 1011. Overlapping targets are allowed. Use a mealy. Do straight binary flip-flop assignment. So straight binary, so 0, 0, 0, 1, 1, 0, 1, 1. All right, so we're in state S0, and we get we're looking for a 1. So if we get a 0, we're just going to stay here. If we get a 1, we're going to go to S1. Here, if we get a 1, so here we're looking for a 0. So if we get a 0, we're going to go to S2. But if we get a 1, then we could stay here because we're allowed to have overlapping targets. We'd still have our first 1. Here we have a 0. Here we have 1 and 0. So if we're looking for a 1 now, so if we get a 1, we'll go down here. But if we get a 0, now we've got 1, 0, 0. So we don't have really anywhere we can go except we have to go all the way back to S0. And then now we're down in S3. If we have 1, 0, 1, so if we get a 1, that's our target. So we put our conditional output block there, so Z will equal 1. And so now we have 1, 0, 1, 1. So we do have our first 1 in our next possible target. So we can have overlapping targets because our first input is a 1. But we don't have anything but the first one. And if we get a 0, now we have 1, 0, which is actually the first 2. So we could actually go up to here, go back to S2, where we remember that we have 1, 0. But we don't output Z because we never got a target. All right. So does that make some sense?
Yes.
All right, now we want to solve for DA, DB, and Z. All right, for DA, we want all the paths in to every block where the coding for A is a 1. And that would be S2 and S3. So we want to do S2 and S3, all the paths in. So what would that be? Well, so S2, we have 2 possible paths in. One comes from S1. So that would be A prime, B, X prime. So we're going to run out of room there. Let me do that on a separate piece of paper. So our DA then would be, so it's going to be, so our A is going to come in from here. So it's going to be A prime, B, X prime, plus, so that's this path. So that checks off this one. Now this path comes from down here. So that's going to be A, B, X prime. So we're going to add that A, B, X prime. Now we have to account for all the paths into here. Well, there is only one path in. It comes from here. So it's going to be A, B prime, X. Okay, so that's our DA. And our DB, so it's going to equal all the paths into here. There are 2 paths into here, and plus the 1 path here. So I'm going to go ahead, I'll add this one in a minute. Let's do the 2 paths into here. So one of them comes from S0, so that's A prime, B prime, X. plus the path all the way down from here, which is A, B, X, plus, then I know the path from, so that's the two paths in here, and then I have to account for the one path in here, which is A, B prime X. And it turns out I can combine these to get A, X. So then it's just A prime, B prime, X plus A, X. And actually, I think, yeah, I don't know, I think I can drop the A prime over here. I could be wrong. But I think I can. Yeah, I should be able to, using the simplification theorem too. But I'm not going to do that. So don't worry about that. Okay. All right. And then for the Z is really easy. The Z only shows up one place, and that's here. A, B, X. And even if we have multiple paths in, it doesn't matter. We have to start in AB and we wait for the next X, and that's when we output Z equals 1, if it's a 1. So ABX. Okay.
I understand most of it except like the Z one, for instance, is really simple to me, but and then the process of finding D is easy, but how do you actually classify that it's D? Or how do you tell what's DA and what's DB? I can see what.
So remember, what is it? So what's DA actually stand for?
I'm not sure.
Okay, it's the D. We're going to use D flip-flops for our problem.
Hmm.
And that's flip-flop A, and that's flip-flop B, and those are the inputs. And that determines, when the clock hits, that determines the next state for that flip-flop. So that's how we're gonna generate a circuit then. Well, here's what the circuit looks like. We'll just draw the circuit. It's easy. So we're gonna have two flip-flops here. Okay, we'll have a clock. It can be falling or rising, doesn't really matter. We're going to have a DA input for our A flip-flop. We're going to have a DB input. And then we're going to have Q and say Q prime, Q and Q prime. And then this input then has to be all that. So this has to be one OR gate. And we're going to have 3 AND gates. All going in here. And this is going to be A prime, B, X prime. This is going to be A, B, X prime. This is going to be A, B prime, X. So we have our input X coming in, and we'll put it also through an inverter, so we can have X and X prime. And this will be X prime, that'll be X. We'll just connect these up to the X. The A prime will be from our Q prime. So this would just be this fed back in here. The B prime would just be this fed back in there. And the X prime would just be this fed in there, and so forth for all these. And for our DB input, I'll take it down here. We're going to have an OR gate going in here. And we're just going to have 2 AND gates. One of them would be AX, because it's simple. And the other one would be A prime, B prime, X. And then we take our Z. Our Z is just going to equal, what do we say? ABX. So it takes the Q from here. And we have 1 AND gate, A, and our B, and then our X. And that's Z. Does that make sense?
Yes.
That's all there is to it. That's the whole circuit. Now, the interesting thing is, if you wired this up and ran it, it would do what this state machine is supposed to do. It would trigger on 1011. Z would be a 1. And you could have overlapping targets. Pretty cool, huh?
Yes.
Now, obviously, you know, we would use these same techniques to make much more complicated things. But that's kind of the start. Okay, down here, we've looked at this one before. So this is just a sequence detector where we're looking for 101 or 001. Well, so 101 or 001. So if you notice, the last two are the same. So regardless, the first one, you can really think of this as don't care 01 for a target. So the first value that comes in, whether it's 0 or 1, we're going to go to S1. We're going to output Z equals 0 here. And then if we get another 0, we're going to go to S2. Still output a 0.
He's recording it, so he's gonna post it.
What's
We
that?
had a quiz last night for this class, and it was like this, like what he's doing right now.
Yeah, I'm recording it. I will post it. Yeah. Yeah, it's recording. Is that what you were asking, Natalie?
No, sorry, I didn't know I was unmuted. I apologize.
Oh, that's okay. All right, and then if we get the last one, then we go to S3. Since it's a more, we have the outputs associated with the node, so we have to put the Z equals 1 there. And normally we don't write the zeros in, and we don't even write a 1 there, we just write a Z. That means Z equals 1. Okay, so if we get, what it says though is that if the target, if the network should reset as soon as the next value in our sequence is not correct, then we have to reset. I said it a little bit differently here, but I changed that on the test. So we definitely, so we go to S1, and then if we don't get a 0 from S1 and we get a 1 instead, then that's not our target sequence. We're going to go back here and reset. In S2, if we don't get a 1, we get a 0, we're going to go there. And from S3, we're going to consider that S3 is not only target, but also a reset. So on our next input, we're not going to go to S0 because that would throw that input away. Instead, we're going to use that as the first item, whether it's 1 or 0. We're going to go to S1. Because remember, our target is kind of a don't care 0, 1. So don't care 0, 1, that's our target. So from S1, so S0, we go to S1 regardless. From S3, we go to S1 regardless, but we output a 1. From S1, we go to S0 on a 1, then we go to S2 on a 0. And from S2, we go to S3 on a 1, and we go back to S0 on a 0. And all these others, we're outputting zeros. Notice there's only one column for the output. It doesn't depend on X. And that means it's a mealy. Okay, and let's see. All right, let's do this one. So this is a more sequential circuit, as one input X, one output Z. If and only if the most recent input was 1 and was preceded by exactly 2 zeros. I worked this in class on Monday and Wednesday, or on Wednesday, I guess, whenever. So I guess I worked it on Wednesday, both classes. Or maybe, yeah, no, I did the video for Monday, so it's on the video. But in any event, so how does this work? Okay, so we're going to use a more. So our outputs are associated with the nodes. And the only thing tricky here is we have to have exactly 2 zeros. Hang on, let me take off my sweater. I'm warming up here. Okay. Okay. All right, so our first, and I in this particular example, I gave you a bunch of the links. Okay, so complete the state graph can be done with 5 nodes. Remember, 2 paths out of each node. How many flip-flops at a minimum will be needed? Well, so you can do 2 states with 1 flip-flop, 4 states with 2, 8 states with 3, 16 states with 4, and so on, powers of 2. So we have 5 states, so it's going to take 3 flip-flops. It takes 5 nodes since you must have a node that means more than exactly 2 zeros. Yes, that's true. So, okay, so remember, we want to just exactly 0, 0, 1. Good, you output it. 0, 0, 0, 1. No output because you had more than 2 zeros. Then you got a 1 and then 2 zeros and a 1. So that's an output here. 1, 1, nothing. 0, 0, 1, another one. 0, 0, 0, 0, 0, 0, 1. That's nothing. 0, 1, still nothing. You have to have exactly 2 zeros. Okay, we start with nothing. Okay. And we'll, yeah, no zeros. S1 is 1 0, S2 is 2 zeros, S3 is 2 zeros and a 1, and S4 is more than 2 zeros. Because we're looking for the target again is the target is 0, 0, 1, essentially. Exactly 2 zeros, so can't have 3. So you really can't have overlapping targets. Okay, so we start in S0. If we get 1s, we stay here. If we get our first 0, we go there. If we get our second 0, we here. If we get a 1, now we have our target. If we get a third 0, now we're here. Well, 3 zeros or more than 2. All right, if we're in S1 and we get a 1, then obviously we have to go back here because now we don't have a 1 0 and we can't get 2 zeros in a row. If we get here and we get a 1, we have to go all the way back here as well. If we get a 0, then we're going here. And then in S3, where we have a target, if we get a 0, then we could theoretically go here and start on our next target. But if we get a 1, now we have to go all the way back to here on a 1. And this is on a 1. And this is on a 1. Does that make sense? Everybody good with that?
Yes,
Okay.
thank you.
Yeah, and we didn't actually solve it because, and what's interesting is if we had done an SM chart, we could just write our solution. But now we have to do the state table, we have to do the flip-flop state assignment, then we have to do the K maps, and it's just a lot harder, more steps. Here's one with 2 inputs. I'm not going to. The state graph's already been done. You just have to extract it. I'm not giving you a problem like that, so I'm not going to review that. And that covers all the way down through here. So this is the last one. So let's look at this one. Okay, so we have a flip-flop. So using the JK flip-flop pictured, okay, it's JK. Right in the tracing for Q. Here's Q. Each division is 5 nanoseconds. In the timing diagram, assume that the time for the output to change after the active edge of the clock or the assertion of the clear knot is 5 nanoseconds. So notice we have a clear knot. And notice it's got a bubble on it. So is it active high or active low?
Active low.
That's correct. And then on the clock, is there a bubble? No. So the clock is active. The clock is a rising edge clock. Let's mark then. The first thing you should do is take the clear knot and mark where it's asserted. So is it asserted here?
Yes, on the last one.
Yeah.
The one, right?
No,
Yeah.
because it's high here. See, clear is high. But it's asserted low. It's deasserted when it's high. So this is not when it's asserted. So here we want our rising edge clock. We want to keep track of this because these clock edges will not be blocked. But over here, it's asserted. So we're going to hatch that in. which means it's going to keep it, the flip-flop's going to be in a clear state, and it's asserted right here. But it doesn't necessarily take effect till right here. Now, it turns out Q is 0 to begin with, so it doesn't really matter. So it's going to be 0 this whole time, and possibly even there. So here, our rising edges are blocked. Oh, not that one. That one's okay. That one's okay. Now, we know that after the assertion of the clear or the edge of the clock, if it's not blocked, we have to wait 5 nanoseconds. And so that means that we're going to, before anything can change, we have to let this little time elapse. So we can possibly change here, we can possibly change here, and we can possibly change here. So we write here, what are our JK? So J is 1 and K is 1. How about here? What's J? J is 1. What's K? 0, because it went down here. So K is up all this time, and it's up here, but here it's 0. And then here, J is 1 and K is 1. All right, so we remember, we can think of J and K and what a flip-flop does. So 0, 0, 0, 1, 1, 0, and 1, 1. Here it's hold. Here it's clear. Here it's set. And here it's toggle. Okay? So what's going to happen here if they're both 1? Is it going to hold, clear, set, or toggle?
Toggle.
That's right. So what is it? It's 0. It doesn't toggle right on the clock edge because it has to wait 5 nanoseconds. But then it toggles up here, stays up here till here. Now it's set and it's 1, 0. So that's set. So it's going to just stay set. And here it's 1 and 1 again. It's going to toggle. So now it'll go down to 0 and stay there. Okay.
Yeah, I got that.
Now, if you have it a little different, let's say we have a set knot. It's asserted here. So you come in, it's going to be low, then it'll go set. It'll stay up all this time. And here it's 1, 0. So it'll stay set. Here it's 1, 1. So it'll toggle down like that. But these clock edges are, oops, I messed up. This clock edge is not blocked. It's good. So I should have done this. And it's 1, 1. So it should toggle down, stay down, go set, and go down. So this is wrong. I made a mistake on that one. All right. Well, anyway. Okay. I think that's pretty much what I wanted to cover. All right. So what questions do you have besides what I've covered?
I had a few questions about the exam date and such.
So it's Tuesday, all day. There are 100 questions. You'll have 2.5 hours, I think is what I lined up.
Okay, good. Thank you.
Yeah, maybe. Yeah, I think 2.5 hours is what I'll give you. I haven't set it up yet, but I'll give you 2.5 hours. And then for DS folks, they get 5 hours. You can start at any time up until 11:59.
Awesome. Thank you.
All right. Any other questions? All righty. I will post the video on both the A and B course websites. And it'll just be Zoom review F22. Okie doke.
Sounds good.
All
Thank you
right.
very much. Appreciate it.
Yeah, sure thing.
Thank you, Professor.
Mm-hmm. Oh, wait, I need to turn off the video, the recording. Let's see. Stop recording.